Hello, I'm Andy Briggs and welcome to the Amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre or simply interesting. Hello listeners and welcome back to the Amazing Astronomical Alphabet with me, Andy, and my esteemed co-presenter Daz. How are you, Daz? Another good week?
Yeah, another good week. The weather's a lot cooler for us, but we're supposed to be getting some rain soon, so and I understand you've already got it.
Yes, well, August is our sort of stormy season. The last few years it hasn't been actually, but it looks like August has started with a bang with the thunderstorms. We've had intense tropical rain most of today, and lots of thunder and lightning. And they've got a poor kitten who's curled up under the table, cowering in fear because it's the first time she's seen rain or a thunderstorm.
Yeah.
So I think she'll be fine.
Yeah.
So we have been swimming in the vast ocean that is the astronomical alphabet, and we've come up again for air this week, and we found a little place, an island with the letter I. So I is the letter we'll be covering this week, and
Yes.
I believe it's my turn to start, Daz.
Yeah, you say the eyes, and we've been swimming. I think we couldn't even describe it as paddling. It's so,
no,
so
that's
few
right.
and far between.
There's a vast astronomical
you to
ocean.
go first.
Yeah,
you to go first, Andy.
There is a vast astronomical ocean that we barely got our ankles wet, but that's the beauty of astronomy. There is just so much to talk about. What I'd like to talk about first of all is I is for, and I'm pretty sure you've got this one, Daz. I is for Iapetus.
Nope.
Oh, you haven't got that one? Brilliant.
No.
Brilliant.
So you start with the moon.
Yes. So Iapetus is a moon of Saturn. It's also sometimes written, for some peculiar reason, as Japetus with a J. So Iapetus is spelled Iapetus, but it's also known as Japetus, Japetus. And this, in fact, you can still see this sometimes. In the book of 2001, A Space Odyssey, the moon is featured, and it's called, Arthur C. Clarke wrote Japetus in that book, not Iapetus. But that's just a little thing. Anyway, Iapetus, we've talked about some really strange moons in the solar system. We were talking about Hyperion last week, the sponge of the solar system. Sponge moon square things. And Iapetus is another weird moon. This one is even weirder than Iapetus. But just to set the scene, do you know who discovered Iapetus, Daz?
It wasn't me.
Yes, I think that's
you'll have to tell me. I'll probably know the name, but
you'll kick yourself. It was Cassini.
Oh, well.
Yes. To be exact, Giovanni Domenico Cassini, with apologies to our Italian listeners, who was born in October 1671. And there was something distinctly odd about his discovery, because he first of all observed Iapetus when it was on the western side of Saturn, and he could see it perfectly. And then he went back when he calculated it would be on the eastern side of Saturn to look at it again, and it wasn't there. And then he waited again till it should have been on the western side of Saturn, and he saw it again. So it was a sort of a disappearing moon. Now, this was very strange. He waited again till it should have been on the eastern side of Saturn, and he had very clear seeing that night. And I don't know, perhaps he had a better instrument, but he saw it. But it was much dimmer than it had been when it was on the western side of Saturn, which is why he hadn't seen it. It was quite substantially dimmer. Now we know that this is because Iapetus has two hemispheres, one of which is dark and the other one is light. It's a very strange thing indeed. Now, if we fast forward to the Cassini probe, which examined, it made, I think, one targeted pass of Iapetus in 2006, I think, if I remember rightly. And we found out exactly why Iapetus has one dark hemisphere and one light hemisphere. Now, the white hemisphere is very bright. It's white as ice, because it is, basically. It's just 100% ice. The dark side is covered with very dark material. And scientists have sort of worked out what it is, although it has to be said that, there are a few ideas, but the leading idea says this. What happened probably billions of years ago now, after its formation, that the leading edge of Iapetus was picking up dust from some of the other Saturnian moons that had been blown off those moons in meteoroid impacts. And this dark material settled on Iapetus. Then what happened was a thing called thermal feedback, because that material, because it was dark, it was absorbing more heat from the sun. And this caused water to sublimate from the ice, which essentially means it turned directly from solid into a gas with no liquid stage in between. And that left a dark residue behind. And the dark residue meant that it absorbed more heat from the sun, and so on and so forth. So it's in a cycle called thermal feedback. And over the eons, the hemisphere has become exceptionally dark with this dark material, which astronomers do believe is the residue from large-scale sublimation of water in the ice. So that sort of put paid to that, which is bizarre because there is nothing else like that in the solar system. But Cassini found something that had never been seen before. There is a ridge directly round the equator of Iapetus. Now, I say equator because it's not perfectly circular. It's like a squash walnut. It's slightly oblate. Well, it's quite severely oblate at the equator. It's fat at the equator. But going right round, or almost right round its equator, there is a ridge. Now, this is exceptionally strange. And this ridge is a ridge of mountains. And they're immense. They're up to 10 miles tall, these mountains. And I remember seeing the images from Cassini and thinking, what on earth is that? For all the world, it looks like somebody's got two hemispheres and welded them together, and there's a weld line around the middle. And that's the equatorial ridge. But these mountains are immense. So obviously the question is, how did they get there? The leading theory says that billions of years ago, Iapetus actually had a ring around it of material that it had accumulated from other moons. And eventually that ring got so dense, the whole ring collapsed onto the surface of Iapetus around the equator. And this is what formed the mountains that we see today. It really is incredibly bizarre. And if you look up the equatorial ridge of Iapetus, the images that Cassini took, a couple of them are just absolutely stunning, of these mountains. They're not very steep. They're more sort of splayed out than pinnacles, if you like. They have a quite gentle slope in many cases. But the ring does go almost the way around the equator of Iapetus. So it's also got a very strange orbit. It actually, although it's the third largest moon of Saturn, it actually orbits a lot further away than the other large moons. For example, Titan. It's got the most inclined orbit of the larger satellites. And another lovely thing about it is, if you think about the other moons orbiting Saturn, they orbit in the ring plane, basically. Yes. So from those moons, you would see the rings of Saturn edge on. But Iapetus has got such an inclined orbit that you would see the rings arc across the sky, which must be an amazing sight from the surface of that moon. And it's just an amazing moon. It's not an incredibly big moon. It's got a mean diameter of about 1,600 kilometers, if I remember rightly. And I say a mean diameter because it is this sort of egg-shaped, if you like. So the mean diameter is about 1,500 kilometers. So, you know, it's sizable. It's a lot larger than many of the moons of Saturn. But it is one of the solar system's most bizarre moons. That ridge system, by the way, we know it's ancient because it is heavily cratered. It's, you know, it's definitely a very, very ancient feature. And there are, you know, some amazing sights to be seen along that ridge. And I can imagine, you know, explorers of the far future wandering along that ridge, exploring. That would be a fantastic thing to do. So there we are. So that is basically it for Iapetus, Daz.
Yeah, exactly. I mean,
an intriguing and unique moon of Saturn.
Exactly. To have two such variations in albedo, which is how much light is reflected off the surface of these of the moon.
Yes.
As you were talking, I've got some pictures here now, and you can definitely see it. And as you said, you can see the ridge around the equator, and it does look like a walnut.
It does. It really does look like a walnut.
But also, I did notice on the really bright side of this picture that I've got here, again, these are Cassini images, there is a massive crater. In fact, there's two. There's one overlying another crater, and they're absolutely huge.
They are. They are.
And they have a peak in the middle. Well, it almost looks like gentle hills in the middle. So it's a fascinating, when you look at it, it's a fascinating moon in itself.
It
but
is.
The difference in albedo, on the high side, it's 0.5 to 0.6 in the albedo rating, which means 50 to 60%, if you remember.
Yes, 50% of the sunlight is reflected from it.
That's right. And on the low side, it goes down to 30%, which is actually quite higher than it actually looks.
Yes, but it's still a big difference.
Yes, it's a fascinating moon, and I'll recommend that the listeners get on the old Tinternet and
have a look at photos of Iapetus. It's gorgeous.
Yes, it's
really gorgeous.
And just to see the size of the crater that's on the, I would assume it's the southern hemisphere. It's absolutely huge, and it actually, like I said, it actually partially overlays a one just slightly to the side of it. So it's fascinating. And of course, we've seen this feature before with the equatorial ridges in the moons in Saturn. Wasn't it? Is it Pan and
Pan and the other one?
Can't remember. Atlas.
Atlas, that's right.
Yeah, Pan and Atlas. So yes, as you said, and that's a call. They reckon it's caused by accretion from the rings actually settling onto the equators of the thing.
Right.
So we have seen this before, but not in such a large,
not such a big scale. No, that's right.
Exactly.
I think it underlines, Daz, yet again, that we've gone out exploring the outer solar system and pretty much nothing is as we expected.
Yeah, exactly. Yeah, I mean,
and that's what makes it so exciting. That you know, nobody really knew before the Voyagers, I guess, or pioneers and Voyagers, what to expect, but it's nothing like we could have imagined. The universe. You know, to paraphrase Einstein, you know, it's not only weirder than we imagine, it's weirder than we can imagine.
Exactly.
And everywhere we look in the solar system, we found surprises. And I think the big realization to come out of, especially the Voyager missions, was that the outer moons of the solar system, so far from the sun, you know, for example, from Pluto, you know, the sun is just a bright star in the sky. Imagine that. It's I just can't work. It's amazing. They should, by rights, or so we thought, be frozen, dead, no activity, nothing going on. But then, you know, we got to Pluto and found out from New Horizons that it's a dynamic, changing, evolving world with lots of different processes going on. Whose nature we're only just beginning to unravel, and you know, the outer moons of the solar system. You've got you've got Europa, you've got the water worlds of the solar system, you've got Europa, Callisto, Ganymede, Enceladus, all of which are strongly suspected of having underground oceans, and dynamic processes on the surface. Io, the most volcanic world in the solar system, over 200 active volcanoes all the time, and some of them are massive. And this was the big realization, I think, from the Voyager era and since, that the outer solar system is a dynamic, changing, evolving place where the sun may not radiate much energy that far out, but it's enough to make these worlds alive, just not frozen lumps of ice. And this, I think you'd agree with me, Des, this has been such a voyage of discovery since Voyager. Getting to know these worlds and seeing things suddenly like Iapetus with its ridge that nobody suspected was there. And we'd never seen anything like it on that scale. It's just wonderful. It's just totally wonderful. This is why we need to get back to the outer solar system, because there's so much to learn there.
I totally agree with you. We need to get back out, because I think we're going to find far more discoveries once we move out there. I'm hoping Juice is going to be a real eye-opener.
I think that's guaranteed.
Yeah, exactly. Because there was something I read the other day, which is sort of like you talk about things that are really surprising. And if I can quickly find it, which I doubt if I can, but it's they found two very strange rocks that are sitting in the asteroid belt.
Oh, I saw that. They shouldn't be there.
Yeah, and they're red
colors. Yeah,
red rock. Yeah, like the Grand Canyon, red rock.
Yes.
It's red, but there's no rock in it. That's the beer.
Bloody awful cider as well.
I'll take your word for it. There's two huge red rocks, which are an indication that they're full of complex organic matter.
Yeah.
And they're sat in the asteroid belt. Well, of course, we know that we find organic molecules and things like that out in the outer beyond Pluto.
Yeah.
Was it trans-Neptunian objects?
Yes,
call them?
That's right.
Yeah,
that's right.
Where we get most of our comets and asteroids from. So we're always picking things up there. But they've actually discovered these, or they've caught images of these two red rocks.
And they think they actually originated in the Kuiper Belt. They think they've migrated inwards.
Yeah, they migrated inwards, and they just want, well, how did they do that?
Yeah, how did they do that?
How
did they do that?
And of course, they're sending, is it Lucy?
Yes, Lucy is
out to the asteroid belt, and I'm just wondering whether or not they could, tweak it a little bit to just have a quick peek at these things and see exactly what they are.
Well, we know from Pluto's moon Charon, whose north polar region is red, and these are tholins. These are what you get when you subject exotic ices from methane and nitrogen to ultraviolet light from the sun. It creates this sort of chemical sludge that is red in color, and the chemicals are classed as tholins. Yeah. And that was a huge surprise as well, because the initial images back from New Horizons, of course, were in black and white, and it looked just a dark area, and there's just this big dark spot on the north pole of Charon. It wasn't until they processed the images for color. Oh, it's red. Oh, it's tholins. Oh. So that was that all. Move on, please. Nothing to see here.
Nothing to see here.
But they reckon that's actually come from Pluto. It's deposited from Pluto's atmosphere. So it's amazing. It's amazing. Well, anyway, we always seem to do at least one interesting moon on this program, and there are so many to talk about. So I'm sure we've got many left to talk about as we go through the rest of the alphabet. So that's Iapetus. And just to spell it again for our listeners, if you want to look at the incredible images of Iapetus, which you can find easily enough on the net, Iapetus is spelled Iapetus. So go Google that and look at the images, because they're incredible. And that's
because when you were talking about Charon and this transmission of material from the host planet to the moons, we're finding all over the place.
All over the place.
Yeah, exactly. Oh, that was interesting. I enjoyed that one. That was good. I is for IC 405, which is the Flaming Star Nebula.
Oh no, I haven't got that one.
Yeah.
Tell us about the Flaming Star Nebula.
It is a short one, but it's a fascinating nebula. It says this really colourful, beautiful nebula sits around the speeding runaway star AE Auriga, and is illuminated by a mixture of emission and reflection processes.
Right.
Rippling dust and gas lanes give the Flaming Star Nebula its name. The orange and purple colors of the nebula are present in different regions and are created by different processes. Visible light from the central star is reflected and scattered by the fine dust particles within the nebula, which tend to bend shorter wavelengths more than larger ones, and therefore give the light deflected towards the Earth a blue tint.
Right.
Then we've got, meanwhile, invisible ultraviolet radiation energizes the nebula gas atoms and molecules, causing them to emit radiation at visible wavelengths as they return to their normal state, which gives us the red light. And how it does this is the bright star of AE Auriga, that's what I wanted to say, Auriga, is so hot, it is blue. It's so hot, it's blue, emitting light so energetic, it knocks electrons away from surrounding gas. Right. When a proton recaptures an electron, red light is frequently emitted. So what we, of course, with these blue and red lights, different colors mixed together, and we get purples. And I recommend that our listeners get on Tinternet again. You've got a lot of homework to do.
Yeah.
And you look for IC 405, and you will see all these colors. And it is such a pretty nebula.
I'm just going to have a look now, Daz, because that's not one that's familiar to me. So I'm just going to have a look. Yeah,
it was just one I came across by accident when we were looking for something to do, and I thought, there's some IC numbers. Let's see if there's anything IC designation.
Oh, that's beautiful. That is beautiful.
It really is, and when you get the colors coming through. As you said, you get the blue, the red, and then they mix together. You get purple, you get orange, and of course, it's these colors that give it its name, the Flaming Star name. So that was just a quick one. I thought I'd start us with.
Any idea? Are we talking about a bright object or a nearby object? Is it something that people could see with small telescopes? I guess not.
Yes, it can be viewed with a small telescope.
I can.
And it's in the let me just
in Auriga, no?
Yeah, it's the purple region color is a mix of the red and the blue light, but reflected just around it. The two regions are referred to as an emission and a reflection nebula, respectively. Officially known as it lies about 1,500 light years distance, spans 5 light years, so it's not a small thing, and is visible with a small telescope towards the constellation of the Charioteer, which is Auriga.
And I've just seen here that it's got a magnitude of +6, so it definitely can be seen in small telescopes.
Yes, it's
interesting.
It's around +6 and all that. So that was IC 405, the Flaming Star Nebula.
The Flaming Star Nebula, another one to have a look at. I've never seen that one. I'm going to go and next time I get the telescope out, I will go and have a look for that. Yes, so, thank you for that adding to our repertoire of nebulae. So, my next one, I is for infrared astronomy. Now, I want to look at it from a particular angle. I want to set the scene for our listeners. You may be aware that we as humans can only see a small part of what's called the electromagnetic spectrum, a very tiny part. And everything on the electromagnetic spectrum is referred to by scientists, astronomers, astrophysicists, physicists. Everything on the electromagnetic spectrum is referred to as light. And the bit that we can see, we refer to as being at optical wavelengths, but it's only a tiny fraction. So you've got everything going from radio waves, low frequency waves, right through to the highest frequency, which are gamma rays. And between those, you've got X-rays, you've got ultraviolet, you've got infrared. And as I said, we can only see a tiny part of it. We share the planet with animals that can see other parts, like bees, for example, can see in the ultraviolet. And plants have evolved to reflect ultraviolet light from the sun at those wavelengths so that the bees are attracted to them. Incredible. What I want to talk about particularly is infrared. Now, infrared, you might know otherwise as heat. We perceive infrared radiation as heat. So when you feel heat from the sun, from a fire, whatever, it's infrared radiation. Your TV remote control uses infrared, which is a pulse of basically heat, but it's all light. It's all classed as light. What I want to talk about with infrared astronomy is the James Webb Space Telescope, which is an infrared telescope. Now, perhaps we'll come back next week with Jay and talk about the James Webb Space Telescope in a bit more detail. But I wanted to ask the question, why the James Webb Space Telescope, which is meant to launch on October the 31st this year after years and years of delays and setbacks, why is the JWST an infrared telescope? If you read people talking about the JWST on the internet, it seems a lot of people had the expectation that it's going to be a successor to the Hubble Space Telescope, that we're going to see the same types of images, only better, with the JWST. This is not the case. The Hubble is an optical, mainly optical telescope. It can go a little bit into the infrared, but it's mainly an optical telescope. So all of the Hubble images that we've been familiar with for 31 years are optical images, most of them. The famous images like the Eagle Nebula, the Pillars of Creation, that image, you know, everything that we associate with Hubble is an optical image. But the problem is that the JWST is an infrared telescope for a few good reasons. Its primary mission is to examine the early universe, the first few 100 million years after the Big Bang. It's an epoch about which we still know very little. We don't know, for example, exactly how the first stars and galaxies formed. We don't know how the first supermassive black holes formed at the centers of those galaxies. There's a lot we don't know about how the universe developed in the first few 100 million years of the Big Bang. The JWST, unlike Hubble, will be able to look back that far. And the reason that the Hubble can't look back that far is because the light from the very early universe, by the time it's reached us 13 point something billion years later, it's been stretched by the expansion of the universe to infrared wavelengths. So to longer wavelengths. So this means the Hubble, being an optical telescope, or largely optical, can't look back far enough. The James Webb Space Telescope was specifically built to be an infrared telescope that could see this light from the very early universe. And that's why it needed to be an infrared telescope. It does also, another thing about infrared is that infrared light from the universe doesn't really get through our atmosphere. It's sort of stopped by the atmosphere. And also, when we look at, for example, the center of our galaxy, it's obscured by huge amounts of interstellar dust, enormous clouds of dust, which means we can't, with optical telescopes, see the center of our galaxy. Now, the JWST with an infrared telescope, you can see right through that dust as if it weren't there. So we'll really, with the James Webb, be able to see lots of things that have been concealed behind cosmic dust up until now. And this is very, very exciting. So this is why the JWST is an infrared telescope. Another thing about the infrared is that it will be able to image the atmospheres of exoplanets directly to see if there are any biomarkers, that is, signs of life. So what we'll be looking for in the atmospheres of those planets orbiting other stars is telltale signs of life. For example, methane, oxygen, things like this. And if you've got those in the atmosphere of a planet, although it's not definitively certain that they are due to life, it's a good indication that there are biological processes on that planet. Methane, for example, you can get from volcanic processes, but mainly on this planet, it comes from life. So these are the fantastic things that the James Webb Space Telescope will be investigating. The ability to see exoplanets directly and hopefully with some ease as well. It's going to be easy to see these planets orbiting other stars with the infrared capabilities of the James Webb. We are about to enter an incredibly exciting era of astronomy and discovery and learning about the very early universe, and finally get to understand, if all goes well, exactly how and when the first stars and galaxies formed in the universe. So there you are. So that's a brief dig into infrared astronomy as regards the JWST. I'm sure, Daz, like me, you're praying that it's going to launch on time and that we don't have another today.
Yeah, and I'm dreading those, was it 15 days of terror?
Yes, absolutely.
They talk about the 7 minutes of terror when something lands on
Mars. Yeah. This is the 15
the James
days
Webb's going to take 15 days, where it's once it's out to its Lagrange point, is everything's going to click into place. It's going to hopefully everything's. I mean, there is. I think when we were talking to a chap who was one of the designers and one of the engineers on there, I think there's 200 single action things that have got to happen.
Yes.
That for it to actually all click into place.
Yes,
it's got to unfurl that great big mirror, which the foil mirror, which is the size of a tennis court. And this is what a lot of the hold up was about, to get it to unfurl without tearing and things like that. And hopefully it'll work better than we expect, because once it's out in space, it's going to be zero gravity.
No, absolutely.
Yeah. So it's not going to have the weight problems that it's had here.
No.
And things will move smoothly. And some people have also asked, well, if it's so sensitive, and we can, as you said about the exoplanets, could it look at the atmospheres of the solar system planets or the moons and things like that?
Yeah.
The problem is that you've got an infrared telescope that's designed to look at wavelengths and look at things so far back in time and so far away, that if you look at anything nearby, it'll be like basically pointing a searchlight in your face.
Yes, that's right.
So it won't be able to be used for close imaging or anything.
No, the radiation is too bright, basically.
Exactly. So what we'll be doing is we'll be looking further back in time, back into history, when the universe was first starting to fire up and form galaxies. And it's just an exciting time. I can't wait. I mean, we're not going to, even once it gets out to its Lagrange point, we've probably still got a good few months before, once they've got to calibrate everything and things like that. So, it's going to be a few months before we get
the first results.
Results, but it's such an exciting time.
I mean, it is, if it does manage, I don't doubt that it will get to the Lagrange point, where it's going to be observing from 1 million miles from Earth. But those 2 weeks afterwards, where it's got to unfold itself, and all those things, as you said, have got to happen in exactly the right time and exactly the right order, and it's got to work first time, because there won't be any shuttle servicing missions like there was with the Hubble.
Exactly.
Something goes wrong.
So far away,
If something goes wrong, the telescope is lost, essentially.
Not like with the Hubble, when we were able to pop up and replace.
No, that's right. That's right.
Give it a pair of glasses so it could see
ring tech support, get a few guys out. And,
that's right.
But it's not going to happen with the James Webb. But perhaps we'll talk about the James Webb in a bit more detail when we talk about when we get to Jay next week, because that will be a prime subject for Jay. Okay, back to you, Daz. I is for
intra-cluster mediums. Basically, what this
fortune tellers,
yeah, mediums, yeah. But it's interstellar. I will get it right. Intra-cluster mediums, and what this is it's the gas that fills the space between galaxies in galaxy clusters. Now, we've mentioned before that with the hunt for dark matter, that this played an important part in confirming that dark matter, or whatever dark matter is, actually exists. As part of it, it started basically dark matter makes stars orbit oddly. Vera Rubin and Kent Ford of the Carnegie Institute of Washington, D.C. were studying the motions of stars in hundreds of spiral galaxies when they obtained results that seemed to fly in the face of conventional physics. A typical spiral galaxy resembles a flattened fried egg. Well, we all know that. With most of its visible mass, stars and bright nebulae, seemingly concentrated in the yolk. Astronomers call this the bulge. Images revealed that the visible mass of the spiral diminishes rapidly with increasing distance from this bulge. Astronomers presumed that the stars in this spiral galaxy orbit around a galaxy center in the same way that planets in our solar system are orbiting the sun. Obeying Newton's law of gravity, the outer planets such as Uranus and Neptune orbit the sun less rapidly than the inner planets. Well, we've discussed this before.
Yeah, we did.
Such as Mercury and Venus. Therefore, stars on the outskirts of a spiral galaxy should orbit at a lower speed than stars nearer the center. But that's what Rubin and Ford found. In galaxy after galaxy, their observations revealed that outlying stars orbit rapidly, just like the inner stars. With so little visible material in the outer regions, how do the outlying stars manage to zip around so fast, still stay bound to the galaxy? They should escape from their galaxy given their speed. Rubin had found serious hints of this unexpected behavior in earlier work, but many astronomers needed to be convinced of it. After the findings of Rubin and Ford became well known, astronomers concluded that visible matter, the stars and luminous gas that show up on telescopic photographs, make up only a small portion of the total mass of spiral galaxies. Although the visible mass is indeed concentrated towards the center, a vast quantity of other material must extend far beyond. Each spiral galaxy is surrounded by an immense halo of dark matter. And to exert enough of a gravitational tug on the stars in the visible outskirts of the galaxies to make them orbit as rapidly as observed. The dark matter must exceed the visible matter by a factor of 10 in mass. Other types of galaxies, including elliptical and irregular galaxies, also have dark matter halos. Dwarf galaxies, which have even higher proportions of dark matter to visible matter than the larger galaxies. Starting in the 1990s, astronomers who observed clusters, now we're getting to what I was talking about, observing clusters of galaxies with X-ray telescopes. This is, like as I said, this is the gas that sits between the galaxies in these clusters, and it's very hot and very excitable. And can be detected using X-rays. And they use satellites such as Rosat and the Chandra X-ray Observatory.
Good old Chandra.
Yeah, good old Chandra. Mapping huge regions in and around the clusters that glow in X-rays. The glows come from an intercluster medium of thin, very hot gas. The hot gas fills such a huge region that thin as it is, its total mass exceeds the sum of the mass of all the galaxies in the cluster.
Oh, right. Gosh,
so what
that's a lot
they're
of
saying
gas.
is it shouldn't be there.
No.
The thin hot gas would expand away, but it's kept in place at the cluster of the galaxies. Let me try that. But it's kept in place at the cluster of galaxies by the gravitational attraction of a mass that is much larger than its own mass plus the mass of the cluster galaxies.
So something is there.
Yes. The source of the powerful gravity is dark matter in the cluster. This fact is a further evidence that Fritz Zwicky was right in 1933 when he claimed that unseen matter, which we now call dark matter, exists in huge amounts in a cluster. So, as I said, the intracluster, I got it right there, the intracluster medium is a very hot, excitable gas in between the gaps between the galaxies in a cluster, which should, in theory, dissipate and float away, but are being held in situ by something invisible, which is dark matter.
And wasn't it that famous image of the bullet cluster where they identified this positively for the first time, that there was a lot more mass there that should have dissipated, but hadn't. And it's being held there by the gravity of something invisible and undetectable, i.e. dark matter. So
yes, so it's just further proof that there is something that we can't detect. The only reason we know it's there is by its interaction by gravity with baryonic matter, which is everything that we've seen on that.
Absolutely. And if we touch again on something we've talked about before, modified Newtonian dynamics, that can explain the rotation curve of a galaxy, but it has real trouble explaining the gravity within galaxy clusters, where you get a group of galaxies together, like our local group has about 20 galaxies in it. And they are kept, as they are in a cluster. They don't fly apart from each other, and they are held really within a huge amount of dark matter. And MOND, the alternative to dark matter that says dark matter doesn't exist, it's just we need to modify Newton, essentially, can't explain that. It doesn't have a solution for the gravitational dynamics of galaxy clusters. So there we are.
Yeah, it seems to fall down once you get to the bigger scale objects.
Yeah, definitely.
And things like that. So yes, but again, like I said, it ties on to yours that the only way you can see this gas is in X-rays, which is again further down the line from infrared.
Definitely.
So
definitely.
Yes.
Interesting.
So that was intracluster mediums.
Well, thank you very much for that. Very interesting. Right. My next one, I, is for ice giant. Now,
you're okay with that one?
Ice giants are planets. They're a classification of planets. We have two of them in our solar system, Uranus and Neptune. Why are they called ice giants? They are gas giants like Jupiter and Saturn. Those are the four gas giants in our solar system, Jupiter, Saturn, Uranus, Neptune. Jupiter and Saturn consist primarily of hydrogen and helium. That's what most of their composition is. Ice giants are different. They're further out from the sun, they're colder, and they are composed largely of water, methane, and ammonia. Neptune is that gorgeous blue color because of this. Uranus isn't, but that's another story because it all has to do with the difference in temperatures between Uranus and Neptune. But basically, Neptune is an ice giant. It's icy, it's cold, it's beautifully blue. And if you've ever seen the image of the high altitude clouds above the atmosphere of Neptune casting shadows down on the atmosphere, absolutely stunning. And ice giants are just one classification of planets. So within our solar system, we've got the so-called terrestrial planets, which are Mercury, Venus, Earth, and Mars. They're rocky planets. They're made of rock. Then you've got the gas giants, Jupiter out to Jupiter and Saturn. And then you've got the ice giants, Neptune, Uranus and Neptune. And you've also got, of course, other classifications like dwarf planets, of which we have 5 in our solar system. Pluto, of course, was famously demoted to a dwarf planet in 2006. And they are another classification of planets. So that's the sort of classification of planets we have in our own solar system. When we look at planets around other stars, so-called extrasolar planets, we find that there are a lot more types that we've found, or astronomers have found. For example, we've got the hot Jupiters, which are big gas giants, even.
Jazz.
Yeah. Oh, Mr. Spooner. Hot Jupiters are big gas giants that orbit very close to their star, very close. So close, in fact, sometimes they take just Earth hours to go around their star, which is crazy. These are obviously gas giants that have formed much further out from the star. It's impossible to form a gas giant that close to the star. It's just too hot. And they've migrated inwards. And we've got, I think, a couple of images or a couple of detections of these planets where the atmospheres are literally being blown off by the sun and stream behind the planet. And, you know, obviously these planets aren't going to last very long because of that. As well as those, we've got so-called super Earths, which are planets orbiting stars that are bigger than the Earth, but they're still rocky, a few times the mass of the Earth. We've also got lava planets, which are also known as hot super Earths. And these are gas giants that orbit very close to their stars. Or they might be rocky planets, we're not quite sure. If they're rocky planets, this is why they're known as lava planets, also called hot super Earths. And there's also another term for them, which is virtually unpronounceable, which is Chthonian, which is Chthonian. Chthonian planets are rocky planets orbiting very close to their star, exceptionally hot, and probably have surfaces of churning molten lava, which would be fun to visit, obviously. And we've also got mini Neptunes, which are planets, gas giants much bigger than Neptune, smaller than Neptune, what I'm talking about, but they are like our Neptune water planets, but they're small on a smaller scale, and so on and so forth. And there are so many different classifications of exoplanets these days, it's difficult to keep up with them, because wherever we look in the universe, we keep finding new things, which is the beauty of studying the universe, of course. We keep finding new planets doing weirder things. And I think the overriding impression that we're getting now is that our solar system is very unusual, in as much as we have planets in stable orbits that don't do anything radical or strange, or, you know, orbit incredibly close to the stars. And this is, another realization that perhaps our solar system is very unusual. And if it is that unusual, that might explain why we have life on the Earth. And that brings us back to the old question, you know, what planets are suitable for supporting life? And what do you have to have in a solar system in order to make that happen? For example, in our own solar system, we know that Jupiter was directly involved with life on the Earth because it's acted like a cosmic vacuum cleaner, hoovering up all the comets and asteroids that otherwise might have hit the Earth because of its immense gravity. So, you know, you have this relation. The Earth doesn't exist in isolation. You have this relationship between the other planets in the solar system, and things have to be just right, which is why the zone where life can exist around a star is known as the Goldilocks zone. It's the zone where liquid water can exist. It's not too far from the sun, nor is it too close to the sun. And, you know, things have to be just right. And it isn't just the Earth, it's the other planets in the solar system that have to be right as well. Otherwise, life could never have arisen on this planet. The moon, for example, was instrumental in life on this planet getting started, or at least on land, because we have the intertidal zones, the zones between the tides, where life could get a foothold out of the ocean and emerge onto land eventually. So all of these, all of these things make you realize that we're part of a much bigger whole. And for life to arise on this planet, things had to be exactly right in the solar system in general, not just on the Earth. So there you are. So that's getting away from the subject slightly, but that's ice giants. But you have to put all these things in context, of course.
Yeah.
So
I'm sure that's chiffonium that you were on about. I'm sure I played that instrument in the school band. I'm sure
you may well have done. Yeah, was it hot to the touch?
It's as you said with the ice giants and stuff like that. But when you were talking there about the Earth and the Moon, of course, we would have still had some tidal movement due to the sun. But it wouldn't have been so large.
No, absolutely.
But there is a discussion, as you said. For the size of our planet, we have a very large moon.
Yes,
and there is a debate as to how instigating the moon was in actually helping life to form on Earth. Of course, the moon originally formed closer to the Earth.
Yes,
but it has so many effects on us. It acts as a brake, so it gives us what gives us our basically 24 hours. Just not quibble about a few seconds. Gives us a 24 hours a day. Eventually, that will, as the moon slowly moves away, we will slowly start to speed up. So you'll have less hours in the day to do all that work. And it's a very strange. When we talk about the discoveries we're making, when we move out further and further, and as you said, when you look at the exoplanets and you realize that our solar system is very different from what we are seeing, it makes you wonder what is actually needed to make life. And maybe, I mean, I certainly believe that there is some form of life out there in the universe. But as to whether or not it's going to be as well advanced, or well, I say we're well advanced, we don't know.
No,
there could be something far ahead. It's something that we really got to think about. And of course, you were talking about the ice giants and all that, and one of my eyes was the ice line, or which is also known as the frost line. And again, that is a boundary which is about between 4 and 5 astronomical units. Yeah. And of course, one astronomical unit is the distance from the Earth to the Sun. So you're talking about 4 times to 5 times the distance. And we got a boundary, an invisible boundary, which we call the ice line.
Yes.
And we will, once you get beyond there, you get molecules of ammonia, hydrogen sulfide, carbon dioxide, methane, plus water, H2O. All of this actually exists as ice.
Yes.
Well, of course, all of these things have different condensation temperatures.
Absolutely.
Where it actually condenses. So the further out you go, you get more and more molecules that do the freezing. But of course, once, as Randy was saying, once you get it condenses into a solid as it freezes, it gives you solid matter for these planets to actually be able to start to form.
Yes,
the big ice giants and that.
Yeah.
So, it's an imaginary line where basically all these molecules then can only exist as ice unless they're being affected by something like tidal pressures and stresses and that, where sometimes they can actually be they can remain as a liquid deep in a moon or something like that.
Sure.
This as I said, this imaginary line, the ice line, is between Mars and Jupiter, just outside the asteroid belt. So
yeah, that's right.
Of course, then, as you said, that's sort of like the dividing line between
too close and too far. Yeah.
Yeah, and then it's as I said, the dividing line between the terrestrial planets and the gas giants.
Absolutely.
So,
absolutely.
Yeah. So I just thought I'd throw that in there.
No, thank you for that. You know what I would just dearly love to be able to live long enough to see us explore another solar system, to look at the differences and similarities and how processes work around other stars. I mean, you know, whether humans will ever get there, I don't know. But it would be wonderful to just go to another solar system and look at how the planets formed. And, you know, in many cases, we're seeing them form. We're seeing protoplanetary disks around other stars thanks to fantastic instruments like ALMA. And we can see planets in the act of formation. And just to point that out, because I'm of that inclination, no supernatural happenings there. It's all physics. And we can see planets forming. And, you know, it happens over millions of years. It happens over such a long time. And it would be nice to go to a solar system to see ready formed planets and look at their histories and to see what happens on them. That's going to be an amazing adventure for humankind in the far future, if we ever develop a way of getting quickly to across the galaxy. But there you are.
Exactly. Yeah, because I mean, you say we're detecting planets, but they've even think that they're even detecting moons.
Moons. That's right. There was a recent image of a moon in the process of formation around a planet, around another star. I never thought I'd live to see such things, to be quite honest. This would have been science fiction just a few years ago. But we've seen for the first time a moon in the process of forming around a planet, around another star, which is absolutely unbelievable.
I is 4. Now we're playing a bit loose with the alphabet here.
Are we? Okay, go on, play loose.
We're I'm using a first name here, and that is Ing Lehman.
Right.
That's INGE Lehman, LEHMANN.
Lehman rings a bell.
Yeah. She lived between 1888 and 1993. That's a hell of a span. And basically, what she is renowned for, I'll just read this. Ing Lehman overturned the idea that our planet's metallic core is entirely molten liquid. She used mathematics to analyze the way energy released by earthquakes travels through the Earth. She discovered something eternally concealed from it on the naked eye, thousands of miles below our feet. At its center, the Earth is solid. In fact, it is the solid inner core and a liquid outer core.
Yeah.
Ing Lehman is also remarkable is that she is one of the longest lived scientists in history. She lived 104 years.
That's amazing.
Absolutely amazing.
And in those days, it was presumably an even rarer occurrence.
Exactly. I mean, we're talking 1993. She saw a lot in her life because, like I said, it's 1888 to 1993. Wow. So it's absolutely amazing span.
What nationality was she, Daz, with a name like that?
Right, yeah, she was born in Denmark in the Copenhagen on May the 13th, 1888.
Oh, right.
Her father was a physiologist and her mother was a housewife, which is nothing to be ashamed of. But their parents came from prominent families. She was a very shy girl who did not enjoy being in the spotlight. She continued to be shy throughout her long life. This is probably why we don't hear of her.
Absolutely.
She was schooled at a private co-educational school called, excuse the pronunciation, Falaskolen, which translates as shared school. The school was new. It had been founded then when Ing was 5 years old by Hannah Adler, a wealthy woman. The school was unusual that it was both boys and girls, and they all studied the same subjects and played the same sports, which was, again, like you say, is unusual for the time.
It was.
And the children were not disciplined as rigorously, I will get that right, as badly as in the schools of that time. She enjoyed her time at the school, Fachhochschule, but she was sometimes bored because she did not feel challenged enough by schoolwork. In 1906, when she was 18, she passed the entrance exam for Copenhagen University with a first rank mark. So she went into that. She started freshman courses in mathematics, chemistry, and physics at Copenhagen University. And she finally graduated in 1920. It took her quite a long time to get her degree.
Right.
And in 1911, she returned to Copenhagen completely burned out after a year at Cambridge University. She abandoned her degree to do actuarial work for an insurance company. In 1918, she returned to Copenhagen University, graduating with a master's degree in 1920, age 32. So it took her quite a while.
Yeah, it did, didn't it?
She worked in the actuarial department at the Copenhagen University. In 1952, now this is where it starts, she transferred to seismology work with Professor Niels Nordland, who showed her how the internal structure of our planet can be unveiled with earthquake data. She visited several regions in Germany, Netherlands, and France, analyzing to discover new techniques for analyzing the Earth's movements. She was captivated by the field of seismology. Age 40, she obtained a master's degree in geodesy, the science of making measurements related to the planet Earth. She was appointed head of the Department of Seismology at the Royal Denmark Geodetic Institute. And she was responsible for running other things as well. And then, of course, during her life, you had books like Jules Verne's H.G. Wells' Journey to the Center of the Earth, and other science books like that, which basically described other worlds living underneath the ground that we stand on. But she was to disappoint people who dreamed of such fanciful worlds. In 1922, she already knew that seismology data from earthquakes could be used to deduce what sort of stuff Earth's interior is made of. To the dismay of many dreamers, seismologists had ruled out Jules Verne's ideas of other inhabitable world below the Earth's surface.
Yeah.
They figured out that vibrations from earthquakes travel all the way through the Earth. Some travel as transverse waves, which are S waves, and others longitudinal waves, which are P waves. The time these waves take to travel from the earthquake's epicenter to different seismic observations around the world revealed information about the paths that they took. The path of earthquake waves through our planet depends on the materials which the waves pass through and the boundaries between these materials. Excuse me. In 1906, Richard Dixon Oldham analyzed seismic waves from several earthquakes and concluded that the Earth has a large liquid metallic core. He calculated the size of the core, finding it forms the inner 40% of our planet's radius. We now know that the core Oldham discovered comprises of the innermost 3,470 kilometers of the Earth's 6,360 kilometer radius.
Oh, so he wasn't far off then.
No, it wasn't far off. Although Oldham had discovered Earth's metallic core, seismologists still did not completely understand the meaning of the data recorded at their observatories. Lehman and other workers were puzzled about the behavior of the P waves. Earthquake data from the observatories showed that these were not traveling through Earth in the way they were expected to. They were appearing in locations they ought not to be. Lehman had an idea. People believed that Earth, below its crust, was molten. She wondered if our planet's inner core might be solid. If it were solid, surrounded by molten liquid, would that amount to the odd behavior of the P waves? She developed a mathematical model models of our planet featuring a solid inner core and Eureka. Such a planet agreed with the observed data. Lehman was able to conclude that P waves were appearing in unexpected locations because they were being refracted and reflected to these locations by the boundary between the Earth's inner core and the liquid outer core.
Wow.
The inner core, she calculated, had a radius of 1,400 kilometers. So just basically through her mathematical modeling, she was able to deduce that we had.
And isn't that one of the greatest things about science, Daz? That you can look at the observations and have a leap of imagination that says, what would happen if that were true? Does that fit the observations? Yeah. And it takes people like her to do that, you know, to have that imagination. Because I've known people in the past have had the distinct opinion that scientists have got no imaginations. Having an imagination is the primary requirement for being a scientist. Well, thank you for that, Daz. I'm afraid it looks as though time has caught up with us. So we will say goodbye, listeners. Thank you so much for listening. And we hope that you've enjoyed the program and that you'll tune in next week when we will be scaling the dizzy heights of the letter J. Or if you want to put it another way, diving down into the deep ocean of astronomy to find our J's. So if that's not mixing metaphors too much,
jellyfish.
Jellyfish, J's for jellyfish. Lots of those about. All right. Well, thank you for all of that, Daz. That was great. I hope you enjoyed it.
It passes so quick.
Oh, it does, doesn't it? You know, we've got enough material for years. So so we will say goodbye. Until next week, if you would like to email us at any time, you can use my email address. That's andy@astroradio.earth. Tell us something you like about the program, something you hate about the program, something you'd like to improve. Any feedback whatsoever. We'll take anything. So, you know, just to get an idea of what you listeners think, because obviously you're very important to us. So if you've got any opinions about this program, andy@astroradio.earth is the address to mail it to. So until next week, from Daz.
Yes, everybody stay safe, and I'll look forward to seeing you next week.
And to play us out today, we're going to have some more music, but this time bands or artists that don't necessarily begin with the letter I. Hope you enjoy it. Until next week, bye-bye.